Hi guys, welcome to the Code Show. This is Harvest, and today we are going to resolve the longest increasing subsequence problem. It's actually most popular problem in the interviews. Also, it's a complete search problem with a DB. And first, we'll take this example to explain it why we get 4 as an output from these elements. So we will follow this example. We will follow some pattern. We'll follow pattern pick or leave in our solution. So let's explain it here in the Excel sheet. So the first thing, if we have this element, so our code has to decide pick or leave this elements. In every iteration has to decide I will pick or I will leave. And the second thing, you have to update your flags. So we're gonna have one flag, loss maximum number, and we initialize it by the minus or negative infinity. So we will explain it. It's a corner case. So it's a corner case, and so we will talk about it in the code. So our code in the first scenario, we have to we'll decide to back. If we back this because it's the first value, we have to update the last maximum flag. So we are going to pick because it's increasing also, so we have to update our flag, and we are going to leave. We will not take this element because it's not increasing subsequence, so we are not going to update our flag. So, and here we are going to decide to pick because it's increasing, so we have to update our flag, and we are going to leave this element because it's not increasing, and we lost the flag we have, it's equals 3. So in this solution we have 3 picks. So this is the longest increasing subsequence for this scenario. But what is this optimal scenario they are actually looking for? The optimal scenario, they expecting your code to behave like pick this one, and for the first element, so your pick scenario will be equal 0. And here you decided to take a pick, take this one. So you have to update your maximum element, and also you have to leave because it's not increasing, and you have also to leave this because it's another scenario, and we have to pick back here. So, and right here, if we back here, I forget to update, so we have to update it. The value is equal to, and the last thing, we have to pick the number 3 because it's increasing. It's a bigger than the last maximum we have. So our longest increasing subsequence for this example will be 4. So here is our optimal scenario, or here is our optimal path that we are going to take for solving this problem. And this is another example. If we are going to take all the buses, actually you have to take all the elements here because it's already increasing subsequence elements. So the maximum, the longest increase subsequence here will equal 6. So let's start to code this. And here we are going to resolve and taking this recursion approach for solving this problem. So we have to define the first, if we are going to follow this instructions to solve our problem. So we have to define our recursion function right now, and we'll call it DFS. And second thing, we will take what is the recursion state. Our recursion state, it will be integer for position, and this position is the element inside this is the element or the pointer inside the pointer inside the elements. Okay, and second thing is the last element we already picked, the last value we already picked. And the last thing, we will pass this vector, we'll call it items, for example, and we'll pick this items. Sorry, we are going to define the best condition for this method. So the best condition for this recursion to avoid the infinity recursion or the infinity calling. So we have to put a position. We have to put the position, the best conditions. Our best condition will be if the position equal the items dot size will return 0. All right. And the second thing, we have to put two scenarios. The first scenario is leaving. And the second scenario is back. So how our code will leave? So our code will define the leave variable right here. Let's bring in the middle, like we call the DFS again, incrementing the element or our pointer without taking and passing the last element and items without any change. So we are not taking anything. And in the back scenario, we have to define the back scenario. We are calling DFS. Sorry, we'll define it first by 0. And based on what we have, based on what we are going to pick or not. We are going to pick based on if the items of position bigger than our items of our last element we picked. So we're going to pick based on this condition, DFS position incrementing by 1 and sending the position, the pointer or the element or the index of the element we already selected or we already picked. So, and also passing the items right here. And this is what we gained. And if the code entered this, if the code or the compiler entered this example or this condition, actually we are going to increment is that we got a 1 value. We got a longest increasing subsequence. Our longest increasing subsequence increased by 1, 2, 3, 4. This is our counter. All right, and in the end we'll return the maximum between the back and the leave and the back. Right, and here is our recursion code, our recursion function without any DB, without any optimization. So we are going to call it and cover the corner case. So we cover the leave scenario and the back scenario right now. Explain it. Okay, so we are going to use this to handle and cover these two scenarios, the corner case scenario and the DB scenario. So first we are trying to call this recursion function to return it as a result. So this recursion function take the position. The position actually is our element, is our pointer. So we will start with the first element as a position. So, and the second thing, what is the worst element you can have? So the worst case element, as you have to take a look to the constraints. The worst case scenario is minus 10 power 4. So, and this is the worst case scenario, right? And we'll pass this nums. This is a predefined vector, and this is this is the worst case scenario. So we are going to pass the pointer of this element. So we will push back this element, the worst case scenario -4, for example, to just if because if you can see the operator here, it's a less than or equal, so it's gonna be maybe it's minus 10,000. So we are trying to cover this scenario, right? So what is the last? We are going to move to pass the point, the index of this element. So the index of this element is equal dot nums dot size. So as we already increased or pushed back a last element in this vector. So we are going to update this base condition. And here is our case scenario we already covered right here. So let's test it in this example or another example like this. Yeah, we got accepted, but in this constraints we are going to hit the time limit exceeded. So we are going to use the DB to resolve the to handle these constraints. to start covering the last scenario with the DB, and here we have to define first the length for the items or the nums dot size here. So we are going to pass this length as the last element we already take. So, and here's we are trying to push back to these numbers. We have to define a public, or for now whatever, public private and memo array. We have the boundaries, or the if you are logged on the constraints, we can see we have 2,500, so we can increase the element. It's a 2D array. This 2D array actually representing the first array representing the position, and the second array is representing the last element. So we are trying to memset to fill this memo array by -1 size of memo to fill this element by this value, and starting here to do the DB scenario using if the memo of position and of last is not equal -1 that we already filled it by the memset, actually is return the memo of position and the last. All right, this is the first thing in the DB, and the last thing we have to reset this value by the max. And here we already did cover the DB scenario. We can run the code test. Here we are. Okay, all right, let's submit. Before submit, we need to enhance something to just store this result in res, and starting to push to put back the element we pushed back before, and let's submit. And here we are.